Hi, this is Alfozia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is types of relation, the second part. In our first part video, we discussed the types of relations. Void relation, which is nothing but empty relation. Universal relation, reflexive relation, and symmetric relation. So far, we discussed all these topics with examples. Now let us start with the next type, transitive relation. First, let us start with the definition of transitive relation. Let A be a set in which the relation R is defined. R is said to be transitive if AB belongs to R and BC belongs to R, which implies that AC belongs to R. That is A related B and B related C, which implies that A related C, where ABC belongs to the set A. This is called transitive relation. The relation can be said to be a non-transitive if AB belongs to R and BC belongs to R, but this does not imply AC belongs to R. If this is the case, then we can say that the relation is non-transitive. This is nothing but the opposite of this. So these two conditions are same, but this does not imply AC belongs to R. Then if this is the case, we can say that this is a transitive relation. Okay, let me give you one example. Please look at this example in the set A of natural numbers. If the relation R be defined by x less than y, then A less than B and B less than C imply A less than C. This is true because we can see numbers in the set of natural numbers x less than y. Hence, this relation is transitive. Okay, I have taken an example where we have to show that R is a transitive relation. First, let us read the given condition. Let K be a given fixed positive integer and R is A, A, where AB belongs to Z and A minus B is divisible by K, where K is a positive integer. Please read this condition carefully. Now we are going to prove that the R is transitive relation. Okay, first let us take down the given information. We are taking down the given information R equal to A, A such that AB belongs to Z and A minus B is divisible by K. Let A, B belongs to R and B, C belongs to R. We are just assuming these because these are the conditions for a transitive relation. So we are going to start from this. So A, B belongs to the real number set and the relation R, and BC belongs to R. So we can take A minus B is divisible by K for this one and B minus C is divisible by K for the second set. And then we will be doing the addition. If this is divisible by K and B minus C is divisible by K, we can say that A minus B plus B minus C is also divisible by K. For example, let this be an even number and this be another even number. If 4 is divisible by 2 and 6 is divisible by 2, we can say that 4 and 6, if you add these two, 4 and 6 means 10. So 10 will also be divisible by 2. So that's the condition we are going to do here. The same concept. If A minus B is divisible by K and B minus C is divisible by K, then the addition of these two will also be divided by K. So if these two are divisible by K, what we will get? If you open the parenthesis, you will get A minus B plus B minus C is divisible by K. These two will get cancelled out. So A minus C is divisible by K. So if it is divisible by K, what we can say that if this belongs to R, we are saying that A minus B is divisible by K. So we are just going to do the reverse thing. If A minus C is divisible by K, then A, C belongs to R. Am I right? Hence, we have proved that AB belongs to R and BC belongs to R implies AC belongs to R, which is nothing but the definition of a transitive relation. Therefore, R is a transitive relation. Hence, we proved that. Please go through the steps and let me know in case if you get any query in this example. Okay, you can apply the same concept. You can proceed in the same way to prove a relation is a transitive. You should also be familiar with non-transitive relation. If this condition does not proved, in case if you're assuming these two and you didn't get that this is not implying A, C belongs to R, then that type of relation is called non-transitive. The next important type of relation is equivalence relation. Now let us see what is this. Please look at the definition. A relation R on a set A is called equivalence relation if R is satisfying the three conditions: reflexive, symmetric and transitive. Okay, I'll give you a general example with variables and then I'll give you one example with numbers. Please look at this example. Let A equal to Z and define R belongs to A comma B such that 3 divides A minus B. First, let us check whether it is reflexive. It is reflexive as A minus A will always be divided by 3. The set A is equal to the integer, and in the set R, A comma B, we have these elements. 3 divides A minus B. So if you take A minus A, it will also be divisible by 3. Am I right? So this is a reflexive. Now let us check whether it is symmetric or not. If A minus B will be divided by 3, we can say that B minus A will also be divided by 3. Am I right? So what do you mean by symmetric? Symmetric is just like a mirror image, as I said already in the previous video. So this example satisfies the symmetric condition also. Now let's check whether it satisfies the transitive. If AB belongs to R and BC belongs to R, then it means A minus B and B minus C both are divided by 3 according to the given condition. Am I right? So first you have to assume A comma B belongs to R and B comma C belongs to R. After that, according to the condition given, A minus B and B minus C are divided by 3. Same as the proof we saw for transitive. So we know that A minus B and B minus C are divided by 3. So what will happen? If you add these two, you'll get A minus C. So it will be helpful for us to prove this is a transitive one. So now A minus C is nothing but, hence this is a transitive one. So for this example, we proved it is a reflexive, symmetric and transitive. Since it satisfies all the three conditions, we can say that it is a equivalence relation. So the relation R on a set A which is equal to Z is a equivalence relation because R satisfies reflexive, symmetric and transitive. Let me take one more example and explain you this concept. So in the previous example, I showed you what are all the conditions to be satisfied to make a relation equivalence. Now I have taken an example. Here it is not necessary that the relation should be equivalence, but we have to check whether it is an equivalence relation or not. Okay, do you understand the difference between these two? In the previous problem, we are supposed to prove that, but here we are just going to check. Okay, from the definition, R would containing following elements. So A is 1 to 14 and R is A comma B, so it should satisfy this condition, 3A minus B equal to 0. Okay. If you try 1 and 2, take A as 1 and B as 2. Check whether it is equal to 0 or not. 3 times 1 minus 2. This is equal to 3 minus 2. Equal to 1, not equal to 0. So you have to do the trial and error method and check what are all the numbers that satisfy this condition, 3A minus B equal to 0. If you take two numbers from this set from 1 to 14 and use this expression 3A minus B, you should get equal to 0. So if I try this number, I'm not getting 0. Same way I'm going to do the trial for all the numbers in different combinations. So I'm going to give you the set of numbers that satisfies this condition only, 3A minus B equal to 0. So when I did trial and error, only these are the 4 combinations that satisfies this condition. When A equal to 1, B equal to 3. When A equal to 2, B equal to 6. When A equal to 3, B equal to 9. When A equal to 4, B equal to 12. No other combination is giving me 0. Okay, so are you clear with this step? Now let me prove that, let me check whether it satisfies the conditions for reflexive, symmetric and transitive. Reflexive means we should have 1, 1 and 2, 2. 1, 1, 2, 2, 3, 3, 6, 6, 9, 9, 4, 4, 12, 12. But we don't have those numbers. So R is not reflexive because we don't have the numbers like 1, 1, a reflecting one. Okay, let's now check for the symmetric property. Symmetric means all the mirror images of these also should be there, no? 1, 3 means 3, 1 should be there. 2, 6 means 6, 2 should be there. And 3, 9 means we should find 9, 3 there. Same way 12, 4 is also not in this list. So R is not symmetric because we don't have the symmetric images of these sets in this relation. Okay, now let us check whether transitive property is satisfied or not. Transitive means if A, B belongs to R, B, C belongs to R, A, C should be belong to the R. Okay, let me take these two, 1, 3 and 2, 6. Okay, we don't have any relation, no? Okay, I'm going to take these two. So 1, 3 and 3, 9. If A, B belongs to R and B, C belongs to R, there is no 1, 9 here. So transitive is also not satisfied. Am I right? So in this problem we are asked to check whether this relation is an equivalence relation or not. While we are checking for the three conditions, reflexive, symmetric and transitive, not even one of the condition is satisfied. So even if it satisfies one of the condition, we cannot say it is an equivalence relation because all the three conditions has to be satisfied. You should see the properties of reflexive, symmetric and transitive in that relation. If you're missing any one of these, you should say that the relation is not equivalence. Does this make sense to you? You may also get examples where you can determine the relation is equivalence. In those problems you can see it proves the properties of, it satisfies the conditions of reflexive relation, symmetric relation and transitive relation. Hope you are clear with the two types of relations we discussed in our video. Hope you are clear with all the types of relations. In case if you have any query, you can let me know. Thanks for watching. See you in the next video.